Our objective for today is to find partial sums of infinite geometric series and to find the sums of infinite geometric series. This is section 8.4, found in our book on page 435, hence finding sums of infinite geometric series. First, we need to talk about what a partial sum is. A partial sum is where we add up only part of a geometric series. Okay, so when I have an infinite series that goes on and on forever and forever and forever, if I only add up a few of them, that's a partial sum. Again, partial meaning only a few or a part. Okay, and so we've actually been doing partial sums when we've only been adding up like the first 5 terms, the first 10 terms. Okay, so we're only adding up a certain number of them. Okay, so let's go ahead and let's look at the infinite geometric series. We got 1/5, plus 1/10, plus 1/20th, plus 1/40th, plus 1/80th. Okay, and we want to find and graph the partial sums. Okay, so first of all, we want to find and graph these partial sums. So if we find them, when I add up one term, okay, so let's just add one term. So let's go ahead, let's create a table of values, the number of terms we're adding. So here's n and here's the sum, s sub n. So I only add up one term, that means I'm only adding the first term, we'll get 1/5. When I add 2 terms, so we're going to add the first 2 terms. Let's go ahead and let's add them. So we're going to add 1/5 plus 1/10, and we get 0.3. Okay, we'll write these as decimals. So let's get 1/5 as a decimal. We get 0.2. Now let's add 3 terms. So let's add the first 3 terms. So I'm going to add 1/5 plus 1/10 plus now 1/20th. And we get 0.35. Now let's add the first 4 terms. So I need to take my previous sum and add the 1/40 onto it. We get 0.375. Now let's add the first 5 terms. So I need to add the 1/80 onto 0.3875. Okay, and so let's go ahead and let's look at the graph of them. Okay, and see what is happening. Well, it looks like we're getting bigger, but not that big. We're still fairly small. Let's go ahead and I'm going to graph these using my calculator. I'm going to do them in a list. Edit. Let's clear out list 1 and list 2. Okay, 1, 2, 3, 4, 5. See, when I add one per term, we get 0.2, 0.3, 0.35, 0.375, 0.3875. Okay, and let's look at the graph of them. So let's turn my plots on. Let's erase my y1, so just clear that out. Arrow up, let's turn my first plots on, y1. My plots should be set up. We can go to our stat plot, second y equals, to adjust them, but I think they're set for my last time, but I'm going to change my zoom. And I'm going to change it to zoom stat. So let's look here. So it looks like we're going up, but it looks like we're kind of leveling off, and that it might actually start approaching some number. Okay, Excel does a really great job of helping me find that number. So we're going to take a break now and go over, and I'm going to do some stuff in Excel so we can kind of see what's happening in these series. Okay, let's first start by writing the rule for this geometric series. Again, it's geometric, so let's write the rule. Again, our rule is a sub n equals a sub 1 r to the n minus 1. So let's find my first term is 1/5. My ratio, let's find my ratio. So let's take the 1/10 divided by the 1/5, and we get 1/2. So my ratio is 1/2 to the n minus 1. As decimals, this would be 1/5 is 0.2. times 0.5 to the n minus 1. Okay, so we're going to go ahead and use this to come into an Excel spreadsheet. All right, now we're going to use our Excel to actually generate a bunch of these terms and find the sum for us. Excel does great at this. So first let's start here. I'm going to start by labeling this box here as the sum. So I'm going to put the sum of the terms in that box. And here I'm going to put n for the number of terms, and here for the actual term itself. So let's go ahead and let's look. So first term, and I'm going to go second term, third term, fourth term, and I'm just going to keep, and you can actually click and drag down, and it'll keep filling. Oh, no, it won't. Sorry, I misspoke. There's a different way of doing that. 17, 18, let's go 19. 19 terms there. Okay, so then now we're going to use the equation editor part of Excel. If you don't remember from computers, okay, to do an equation, I hit equals. Okay, so now I want to type in the general rule for my equation. So it's 0.2 times, let's do the times button, 0.2. The times is the star, which is shift 8, times, and then we want my ratio 0.5. I guess I don't need the parentheses, 0.5 to the, and then now in parentheses for my exponent, I'm going to take this term, my a sub 4, click on it, and subtract 1. When I hit enter, if you notice, I get 0.2, which corresponds to our first term of our geometric series, because 1/5 is the same as 0.2. So now instead of doing that for each individual term, I can just click this and drag down. And it takes the previous, so there it takes this number, subtracts 1, so it puts a 2 in, it puts a 3 in, it puts a 4 in, just by using that equation, that a4 minus 1. So this one would take a5 minus 1 and so forth. Okay. So let's do, there's the first 7 terms. Let's find the sum of those terms. So now to find the sum, again, I go equals, and I want the sum, and I want the sum of this column right here, this row right here. So let's go ahead and let's click and drag. I want the sum of those, and then hit enter. So when I add them those up, I get 0.396875. And if you hover on this, it has that little error thing. It's just saying you because some of the cells are empty because these ones are empty yet. Okay. So when I add the first 7 terms, I get 0.396875. So let's go ahead and let's add another term. Let's get this 8th term in there. I get 0.3984375. So what does that look like happening as I add more and more terms? What's happening to my sum? 0.39960, 0.39990234, 0.3997559. If we notice a pattern here, it looks as if, 0.3999939, we're actually approaching one solid number. Okay, even closer, even closer. If you notice, these numbers are extremely small. 1.5259 times 10 to the 6th, and so forth. Looks as if this number is getting closer and closer to the number 4. Okay, this is getting closer and closer to the number 4. So actually, this geometric series, geometric series, since it's infinite, is actually getting closer and closer to 4 because these numbers I'm adding are getting super, super, super small. 7.6 times 10 to the negative 7. Super, super small. Back 7 decimal places, 0.0000007. Okay, so my sum is actually getting really close to the number 4. So it's actually approaching one constant number. Okay, and this happens quite often. Okay, so let's go ahead and let's look at, there's actually a tip or trick for finding the infinite sum. As you noticed in our Excel video, the sum of an infinite geometric series with the first term of a sub 1 and a common ratio of r now, here's our shortcut method of finding that sum. We take the first term and divide it by 1 minus that ratio. Again, provided our ratio is less than 1. In class, we're going to look at this ratio greater than 1 aspect. But for right now, if my r is greater than 1, then the series has no sum. Okay, it has no sum if my r value is greater than 1. And we'll look at that in more detail in class tomorrow. So let's find the sum of each of these infinite geometric series. So the first thing I need to do is I want the sum, again, from 1 to infinity, so it's an infinite series. I need to know my first term, and I need to know my ratio. Okay, so first of all, my first term, when I put a 1 into this, okay, so again, you could always put a 1 into this, so we need to find our a sub 1. My a sub 1, when I put in a 1 into this, 4 times 0.2 to the 1 minus 1, which is 0. So my first term ends up being that 4. And again, my ratio is that 0.2. So to find the sum, again, we don't go S sub n because it's a sum of all of them. This isn't just the sum of the first so many, this is the sum of all the numbers in this series. So the sum is equal to the first term divided by 1 minus that ratio. So my first term is 4 divided by 1 minus my ratio, which is 0.2. So I take 4 and divide it by 1 minus my ratio of 0.2. And so when I add these all up, I get actually the number 5. So when I add up all of the terms in this series, I get 5. Crazy. Okay, so let's do another one. So we want to find the sum of each infinite geometric series. So first of all, I need my first term. My first term here is negative 6. Again, these are sums. So this is negative 6 plus negative 4 plus negative 8/3. So negative 6 is my first term. My ratio, to find that, divide one term by the previous. So take negative 4 divided by negative 6. My ratio would be 2/3. Both simplify by negative 2. So now my sum is equal to the first term divided by 1 minus my ratio of 2/3. Oh, we're just writing the equation first. So my sum is equal to the first term, negative 6, divided by 1 minus 2/3. So I'll take my first term, negative 6, divided by 1 minus 2/3. We get negative 18. So when I add up all of these numbers, it makes sense they'd be negative because all of these I'm adding a bunch of negatives. When I add them all up, I get negative 18. Okay, let's look at the next one. Again, my first term is 2. My ratio is, take the previous term divided by the 5/2. 5/2, wait a second. This is bigger than 1. So this has no sum. Again, if that R value is greater than or equal to 1, then the series has no sum. Okay, let's take it. Okay, example 3. A pendulum. So we have, basically a pendulum is something hanging and swinging. So we have something hanging here that's swinging back and forth. A pendulum is released to swing freely, travels 100 centimeters on the first swing. So on the first swing, it's going to travel 100 centimeters total. So first swing, 100 centimeters. On each successive swing, the pendulum travels 96% of the distance of the previous swing. So every swing, it's decreasing by 96%. We want to find what the total distance the pendulum swings is. So each time, again, if you agree, if it reduces by 96% each time, eventually it's going to stop swinging. And we want to know by the time it stops swinging, how far will it have totally swung? Okay. So to do that, again, this is a geometric series. Okay. Because if you think about it, the first time it swings, it's going to swing at 100 centimeters. The next time, it's only going to be 96% of that. So 100 times 96%, 0.96. Okay. The next time, it's going to be 100 times the 0.96, but 96% of that again. If you notice, we're multiplying by 96% each time. Okay, so I want to add these all up. So then my actual general rule, ... is 100 times 0.96 times n, the number of times total that it swings. So to find my sum, again, my first term here is 100%. My ratio is 96% because that's how much it's going down each time. So my ratio is 0.96. So my sum, again, is equal to the first term divided by 1 minus the ratio. So the first term is 100 divided by 1 minus 0.96. So 100 divided by 1 minus 0.96, 0.04. 200,500 centimeters will be the total number of centimeters that this thing will swing. Or if we convert it to meters, that would be divided by 125 meters. Okay. All right. We can actually use this idea of an infinite geometric series to actually rewrite fractions in simplest forms. I know your calculator can do this. I don't want to see if your calculator can do it. I want to see if you can do it. So I need to see the work shown. So here's how you do it. Basically, I'm going to rewrite this as a series. I'm going to break this up into pieces that repeat. The part that repeats is the 0.7. So I can think of this as 0.7 plus 0.07 plus 0.007 plus 0.0007, and so forth. Basically, I just keep moving my 7 back one place. So my first term is 0.7. My ratio in this case would be what? The 0.07 divided by the 0.7. So my ratio, 0.07 divided by 0.7, I believe is 0.1. So my ratio is 0.1 because I'm increasing by 0.1 each time, or multiplying by 0.1 each time. So there's my R. So I can think of this as the sum. First term, 1 minus R. But again, I want this as a fraction. So my first term is 0.07, 1 minus 0.1. So this would be 0.7 divided by 1 minus 0.1, which is 0.9. So I have 0.7 divided by 0.9. If I multiply numerator and denominator both by 10, I get 7 over 9, which guess what 7 divided by 9 is? 0.77777, repeating. So I just found the fraction for 0.7 repeating. Again, when doing this in your homework and in your practice, show the work. You can use your calculator to check it, but I need to see the work up to that point. And now your turn problems. If you notice here, there's a your turn problem here, number 1. You can use your calculator to help you graph this, but this is very similar to example 1. Okay. And then on the back side, I want you to do problem 3 and 5. If we have time, we'll do 4 and 6 in class, and then number 7 and number 8. Come to class ready to discuss.